Good evening to one and all. Is my voice clear? To all? So let us start our today's session. Any queries on the previous class? We have started the concept of subgroups and we did some theorems on it. Later we discussed with the concept of cosets. Any questions or any doubts over this concept of subgroups or cosets to anyone? Please tell. Then, so let us start our today's session. The concept of cosets, which is very interesting for you. Before that, as we know what is meant by a coset, let us do a small problem on this. You take the group Z15 with the operation plus 15 and the subgroup H equal to 0, 3, 6, 9 and 12. Now we are going to construct the cosets with respect to H based on Z5. Now first of all tell me how many cosets we are going to get here. So if you want a formal definition, we define the coset AH is equal to set of all AX such that X belongs to H. If the operation is plus, we define A plus H is equal to set of all A plus X such that X belongs to H. And basically the element A is taken in the group. So one of our friends that we will get 5 cosets. Any more answers from anybody? How many cosets we are going to get here? Right. Now let us write the set first. Z15 equals to 0, 1, 2, 3, so on up to 14. You accept it? Yes or no? Now look at the definition of coset. If you take an element in G, corresponding coset you are generating with H. So the number of cosets is based on the number of elements in G. Here, how many elements are in the group under the set Z15? 15 elements. 0, 1, 2, 3, 4 up to 14. So you will get 15 cosets here. So if you write the cosets one after the other, it is nothing but first coset is 0 plus 15H, nothing but for every element in H you are adding 0 with respect to the operation plus 15. So 0, 3, 6, 9, 12 will come. Second we do 1 plus 15H. So 1, 4, 7, 10, 13. Then we'll go for 2 plus 15H is equal to 2, 5, 8, 11, 14. The next coset is 3 plus 15H equals to 3, 6, 9, 12, 0. Because 12 plus 3 is nothing but 15. Under the operation modulo 15, it is nothing but 0. So we are going to write all the cosets like that. The remaining one, 5 plus 15H, 4 plus 15H, 6 plus 15h and so on, 14 plus 15h. Now I request you to take 1 or 2 minutes of time and write these cosets. Please do it right now. We will have a good discussion on this model. I think you understood how to write these cosets, right? Am I correct? Any digits for anybody, right? You please go ahead. So write down the remaining cosets, 4 plus h, 5 plus h, up to 14 plus h. I will wait for your sign. You take your own time, no problem. So others, as and when you finish, I will ask you questions, your observations on finding these cosets. I will ask you, take your own time and tell. After finishing the cosets, you please let me know. Anybody has any doubts with regard to finding the cosets? So one of our hands have done with it. So if you want to find 14 plus h, it will be 14. 14 plus 3 is 17, so you have to take 2. So 14 plus 6, 20, you have to take 5. Then 8. So 14 plus 3, 14 plus 9, 23, so you should take 3. 14 plus 12, 26, you will take 1. If you are adding 14 and 9, the result will be 23, right? So you are doing under modulo 15. So whatever the value come, you divide with 15 and take the remainder. So if you divide with 5, that is a different issue. For 15, your answer is correct. 8 and 11, that was correct. If you take a modulo 5, there is a different issue. That's it. Yeah. So now let us start our observations. So the total number of cosets is equal to 15. It is nothing but order of the group. You accept it or not? The first observation. How many cosets we have calculated right now? The second observation is all these cosets are distinct or some of them are repeated. Are you getting that all the 15 sets are totally distinct or some of them are equal? I will say one thing, that if you take two cosets, you can say that the elements in the two cosets are totally same or they are totally disjoint. Agree? Don't compare with the order of the elements. Don't compare with the order of the elements. Elements order may be different, but the elements are same in two cosets if you compare, or they are totally different sets. Agree? You just take the example that, let us take these two. These are totally disjoint. There is no element common between these two cosets. Agree? Yes or no? Right? Suppose if you calculate the coset 3 plus 15h, what you are going to get? 3, 6, 9, 12, 0. Now you can say that these two sets are equal. 0 plus 15h and 3 plus 15h. These two cosets are equal. You agree or not? So your observation is, if you take any two cosets, either they are totally distinct, no element is common between them, and if otherwise the two sets are totally same, elements order may be different, but the same elements will come. 0, 3, 6, 9, 12, 0, 3, 6, 9, 12. Both are same. Agree? Right. So here the observation is, any two cosets are either identical or disjoint. So another observation is, now see, how many elements are there in the first coset? 5. Second coset? 5. Third coset? 5. So each coset is having equal number of elements, and that number of elements is nothing but the order of the subgroup 5. So order of any coset equal to order of the subgroup. Here it is 5. Agree? Because the subgroup contains 5 elements. If you take any coset, each will contain 5 elements, not more than 5, not less than 5. Accepted? Now let us consider the distinct cosets. This is a distinct coset, this is a distinct one, this is a distinct one. So if you calculate other cosets 3, 4, 5, 6, etc., 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 they may be equal to one of these sets. You are not getting different cosets. Agree? Among the 15 cosets, if you bifurcate them, what are the different cosets, and identify them separately, then these are the elements in the distinct cosets. Now see, if you combine them, if you take the union of these three cosets, you will get the whole group Z15. You can observe that 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, nothing but Z15 has come. So it is nothing but 0 plus 15H union 1 plus 15H union 2 plus 15H. The group is nothing but union of these three cosets. Not only that, you can take other cosets also. 3, 4, 5. The union of these cosets you can take. Accepted? So in one way, you can say that whatever the distinct cosets you are taking, they will form a partition on the group. So what is meant by partition? If you consider their union, it is equal to the whole group. For every operation, the properties what I am saying right now are applicable for every group, every subgroup while calculating the cosets. These are the common phenomena. Now, let us do one simple problem which will give you a good idea. So, are you clear about these properties? Please tell. I will say one more thing. Here, while calculating the cosets, all these cosets are nothing but equal to h. Agree? You can check with your answers. So actually, these properties are applicable for infinite cosets also. But the thing is, since for infinite coset, you cannot calculate a coset, right? Actually, you have read the infinite number of elements in that. So these properties are applicable for finite sets only, the finite groups. Our discussion is confined to finite groups only, not for the infinite. Right. So if you observe that all these cosets are nothing but h, you agree? Now, if you observe that while considering these cosets 0, 3, 6, 9, 12, these are nothing but elements in h. So what it means that if G is a group and H is a subgroup, we are forming the cosets by taking an element in G. So if you take an element A which is outside of H, you will get a different coset. If you take A inside of H, if you calculate a coset, it is nothing but H itself. So the coset and subgroup both are same. If you form a coset by taking the element which is in the subgroup itself. Are you getting the context? In other words, you can say XH is equal to H if X belongs to H. The coset what you are forming will be equal to the subgroup if the element is taken in H itself, the subgroup itself. Did you understand? So these are the good properties we need to understand while proving the theorem that we call it as the Lagrange's theorem. Let us take the statement of the theorem. The order of the subgroup of a finite group divides the order of the group. This is the statement. Please take a note of it, which is interesting, and let us prove the theorem right now. After noting the statement, please tell. Now, here we have taken a finite group and a subgroup of it. So let us take that G is a finite group and H is subgroup of G. So our interest here is we have to show order of the subgroup divides the group order. So if you take values for them, let us take that order of G is equal to M and order of H is equal to N. Let us take like this. So as per the theorem statement considered, you have to show that N divides M. It is our claim, we have to prove. We accept it? Are you getting the idea? So it is enough if we have shown that M is equal to N into some number. So in order to show that N divides M, it is enough if we have shown that M is equal to N into some number. As you know, by taking every element in the group, we can form the cosets. And among these cosets, only some cosets are distinct, remaining are repeated. And one more interesting thing is, if you consider the distinct cosets separately, the union is nothing but the total group G. These observations we have made just now. So let us incorporate these observations here in the writing format as, so in the total M cosets, assume that K cosets are distinct. And we know that their union equal to G. So here we can write that G is equal to H union, HA union, HB union, so on, K cosets. You agree for this? Now let us apply or let us calculate the total number of elements on both sides. So this implies order of G is equal to order of H plus order of HA plus order of HB plus so on, K cosets. This thing I have written directly because actually you have a formula N of A union B is equal to N of A plus N of B minus N of A intersection B. Did you recollect this formula from school level? Say, if A and B are totally different sets, there is no element common, then in that case, N of A and B is nothing but N of A plus N of B. The intersection part we will omit because these are totally different sets. Here also, all these sets are totally different. So there is no need to consider the intersection part separately. Hence we will write like this. Is it okay now? Why I have written like that? So from this equation we can say order of G is equal to M. This equals to, as we know, order of H is N, and every coset contains the number of elements equal to the number of elements in H. So this is nothing but N plus so on K times. Therefore, you can say that M is equal to N into K. Therefore, N divides M. We can say that order of H divides order of the group. So if you understand the properties of cosets fundamentally good, then this theorem is nothing but a cakewalk. Okay? Any questions or any doubts or the proof of this theorem to anyone? Please tell. So if it is clear, I want to take the other parts. I will erase the proof of the theorem. Can I? Right. So here we can say one more thing, that here order of H divides order of G. So we can say order of H is the divisor, order of G is dividend, and you will get the quotient here. As N divides M, you will get a quotient. So from this expression, K is the quotient. So this K gives what? The number of distinct cosets formed with respect to H. So at this point, we will define a small definition. At this point, we will define a small definition that index of a subgroup. Symbolically, we write it as G is to H, and we will write it as order of G by order of H. Some others use the symbol as index of H with respect to G. So index of the subgroup H with respect to the group G. So this is nothing but order of G by order of H. So the total number of distinct cosets, what we are getting, that is denoted as index of the group. Okay? You take a note of this definition. And for every theorem, there are certain limitations. So the concept of Lagrange's theorem is applicable for finite groups only, not for infinite groups. Another thing is, the converse of the theorem is not true. In the theorem, what we are doing, if H is subgroup of G, then we are proving that order of H divides order of G. So if you talk about the converse, if H is a subset such that order of H divides order of G, is H subgroup of G? This is the converse of Lagrange's theorem. So this is not true, because we will take a simple counter example that you take G is equal to 1 minus 1 I minus I, and H is equal to the subset I comma minus I. So it is clearly evident that 2 divides 4. So order of H divides order of the group. But H is not a subgroup of G because the closure law not satisfied. As you know, I into minus I is nothing but 1, which does not belongs to H. So the converse of the Lagrange's theorem is not true. I mean, not always true. And the theorem is applicable for finite groups only, not for the infinite groups. Is it sufficient for you? Shall I continue? Right. So one application of Lagrange's theorem is a finite group cannot be expressed as union of two of its proper subgroups. You please take a note of this. We will discuss on this model. A finite group cannot be expressed as union of two of its proper subgroups. So for this, let us take G is a finite group and order of G is equal to n. Let us take. And say H comma K are two proper subgroups of G. So as per the problem view, we have to prove that G is not equal to H union K. This is our actual claim. We accept it. So we have to prove this statement. Since there is no direct proof, we use the technique of proof by contradiction. So if possible, let G is nothing but the union of H union K. It is possible. So every lecture is totally different. So there is no need to follow the previous lectures. From right onwards, you can follow them. You need to observe the previous class, that is enough. Prior things, you can watch them at your free time. Okay. So let us assume that if possible, G is the union of the two subgroups H and K. Now, while doing the process, we will get a contradiction. So we can confirm that G is not equal to union of H and K. Right? Now the question is, here you have taken that H and K are proper subgroups. So what does it mean? The proper subgroup concept? What is meant by a proper subgroup? So that are not trivial. In a simple manner, you can say, if you take a group G, the trivial subgroups are identity and G itself. So H is a subgroup which is bigger than identity and smaller than G. Similarly, K is also a subgroup which is bigger than identity and smaller than the group G. Agree? This is the statement of proper subgroups. Just now we have proved that order of the subgroup divides order of the group as per Lagrange's theorem. So you can say that order of H divides order of G and order of K divides order of G. It means that order of H divides N and order of K divides N. Right. Now let us think about the statement what you have written now. So you have taken that G is equal to H union K. Now see, as and when you take the subgroups, every subgroup contains the identity element, isn't it? That is by default common. The identity element is unique. Now, from this representation, for our understanding, let us take some numbers. Right? Now tell me, you give a number for order of G. You give a number for order of G to me. Follow. So, if you observe that this is H and this is K, so every subgroup contains the identity element. So the intersection contains identity. Now what happens? H and K may have common elements or different elements that I don't know. So from this perspective, if you remove one element, you will have 11 elements remained in the group. So these 11 elements will belong to H and K in any manner. So H contains 2 values, K contains 9 values, or H contains 3, K contains 6. K contains 8. Any manner you can say. You accept it? So that total number of elements will be equal to 12 because G is equal to H union K. You accept it or not? Right. Now, if you observe that while writing this way, let us fix one pattern. Among these patterns, you fix one pattern to me. You give how many elements are there in H, how many elements are there in K. You give numbers as per your vision. You tell me how many elements are there in H, you give a sample number to me. Can I take 3? So if I take 3 elements, we can take 2 elements in the intersection. That is also correct. That I am not objecting that. That is also true. No wrong at all. So you are saying that H and K contains common elements, right? So you give some numbers so that common elements are, let us take. So if you take a big picture, say this is H and K. So you give common elements to me. You have to give some common elements. Identity is common. Can I take 3 more elements are common for both H and K? Let us take like that. Right. Now you give me total cardinality of H. You can take anything. So already 4 elements are there in H. You give me some other number. I will fix this is the total number of elements in H. Can I take 5? So what happens? 5 plus 3, 8, 8 plus 1, 9. So order of H is equal to 9. So if it's from this perspective, you can say that 5 plus 3, 8, 9. So this could be how much if we consider the part remaining 3. Then only you will get 12 elements. G is equal to H unit K. Accepted? All of you getting the idea or not? How I am writing like this? So order of K is equal to 7. Now, is these statements correct or not if you take like them? That is also true. You are perfect. Let us take the case also. H, K. So 4 here, 4 here, 4 here. That is perfect. So here order of H is equal to 8, order of K is equal to 8. So whatever the case you consider, is this statement a valid one or not? Is Lagrange's theorem hold good in this case or not? It is totally opposite to the case of Lagrange's theorem. You accept? Order of H divides order of G is not satisfying as per the numbers you have taken. Yes or no? Right. So if you take the other thing, let me say the previous thing I have taken. So this H and K you take. So here I have taken identity. Here I fix 3 elements. So 3 plus 1, 4, 4 plus 8, 12. So order of H is equal to 4 here. Order of K is equal to 9 here. So if you consider this case, what happens? Order of H divides order of G is correct. Order of K divides order of G is not correct. So if you observe that, while whatever may be the pattern of the elements for H and K, either the elements may be totally distinct or they have so many common elements, etc., etc. Whatever the case you consider, obviously you can observe that in one of the sets H and K, one set must contain exactly more than n by 2 elements. Here you observe that the two sets, order of H, order of K, both are having more than n by 2 elements. Here n is equal to 12. N by 2 means 6. So here order of H is equal to 4, which is less than 6. Here order of K is equal to 9, which is more than 6. So whatever the segregation you will do. So if you say that what happens if H is a subset of K, then K is nothing but H unit K is equal to K, and this is nothing but G. That means that G and K both are equal. Then H and K will become trivial subgroups of G. Please understand. Trivial subgroups. That's why that case won't happen. So definitely H is not a subset of K and K is not a subset of H. Because you have taken that G is equal to H unit K. So the whole discussion by taking numbers, why I have chosen that, I want to mention that whatever may be the elements pattern in these sets, obviously one set will contain more than n by 2 elements. That is possible. So if you write the divisors for n, 1, 2, 3, so on, the maximum proper divisor is n by 2. So if I am considering the divisors of 12, you can take 1, 2, 3, 4, 6, then 12. 6 is nothing but n by 2. So you cannot get a divisor more than n by 2, a proper divisor. You accept it? So here we conclude that in the formal writing, we will mention that we have E belongs to H intersection K. So one of H and K will contain more than n by 2 elements. So order of H divides order of G will not be satisfied for one subgroup. Therefore, it is a contradiction to Lagrange's theorem. Hence, G is equal to H unit K is wrong. The solution of the problem is very simple, just 4 lines. If possible, let us assume that G is equal to H unit K. So we will say that identity belongs to H intersection K. So one of H and K will contain more than n by 2 elements. That may be either H or K. So subgroup order divides group order will not be satisfied by one of the sets, at least one of the sets. So it is a contradiction to the statement of Lagrange's theorem. Hence, G is not equal to H unit K. It means that whenever you take a finite group, you cannot represent it as union of 2 proper subgroups. It may be 3 proper subgroups accepted, but 2 it is not correct. Okay? Is the ideology clear for everyone on the whole? Right. Now, at this point, we define one more problem. I mean, a definition we can call. So we can say like this. A group of prime order has no proper subgroups. A group of prime order has no proper subgroups. It is also an application of Lagrange's theorem. Let us say order of G is equal to P, a prime number. So what happens? Is it an extension of the general theorem we did previously that the union of 2 subgroups is a group only if one is subset of the other? No, it is totally different version. We are not at all considering that. There is a different issue, there is a different issue. Don't mingle subgroups and cosets. We are thinking and doing totally different. So for every chapter, we will have new results, new problems. We don't bother about the previous ones. All are totally different. You cannot say the interconnectivity. You can have the interconnectivity while using the theorem statements. That's all. No separate connectivity at all. So if you take H is any subgroup of G, you take any subgroup for G, say it is H. So by Lagrange's theorem, we can say order of H divides order of G. It implies that order of H divides P. Since P is a prime number, the only divisors for P are number 1 and P itself. Therefore, order of H must be either 1 or order of H is equal to P. You don't have any other possibility. You accept it? So, if order of H is equal to 1 means H contains identity element only, because you cannot form a subgroup without identity element. So if we say that order of H is equal to 1 means H contains only one element, that is nothing but identity. If you say order of H is equal to P means subgroup and group both are having same number of elements. In this case, it is nothing but H is the whole group itself. So you can observe that if you take any subgroup for the group, it is becoming equal either to the singleton set or the whole group. So you are not getting any set which is bigger than identity and smaller than G. So the only subgroups are nothing but identity and G itself. So these are trivial subgroups. So we can say that whenever a group of prime order you consider, you cannot have proper subgroups. It will contain only improper subgroups. That is the conclusion. Okay? Please take a note of that. Now I want to give some results for you. You please take a note of them, which are useful while solving the other results in the next chapter. They are useful in the next chapter. And I am going to prove two results right now. Remaining I will give as a note conditions for you. You can note them and we will make use of them. There is no need to write the proofs for them. They are not required. So can I erase this? You please take a note of them. Then we discuss the approach. So I have taken two elements A, B in the group G and H is a subgroup of G. You can take any subgroup H. So what he is saying, HA is equal to HB if and only if AB inverse belongs to H. It means that if you calculate the right cosets with respect to A and B, if the cosets are equal means this element must belong to H. A into B inverse belongs to H. Similarly, if you say that the left cosets are equal, then A inverse B must belong to H. It is implied and implied by condition. Okay? Similarly, if you say that the element A belongs to the left coset, then corresponding left cosets are equal, AH and BH. If the element A belongs to the right coset, then respective right cosets are equal, HA and HB. You please take a note of them. Shall I continue? So earlier, while observing the properties of the cosets formed, we made a resolution that if you form a coset by taking the element in the subgroup, then coset and subgroup both are equal. Can you recollect that? The example what we did earlier, I will say that 0 plus h, 3 plus h, 6 plus h, 9 plus h and 12 plus h. All these cosets are equal to h. You agree or not? So this I have confirmed because h is nothing but the set 0, 3, 6, 9, 12. So if you form a coset by taking the element in h, then coset and group both are equal. Is it clear? So this thing we want to prove it theoretically right now. Let us prove it theoretically. So what is our intention here? X belongs to h if and only if the cosets are equal. You may take left coset or right coset, whatever the case may be. If the element belongs to the subgroup, coset and subgroup both are equal. Let us prove it theoretically. So it contains main part as well as converse part. Let us prove them. So if you take the converse part, you assume that xh is equal to h is equal to hx. So what is our claim here? We have to prove x belongs to h. Now, basically x belongs to G, accepted? Because every element will be in the group G. Yes or no? Right. So we can say that x can be written as x into identity. So this part belongs to xh. Because what is the pattern of the cosets? xh means x into something that will belong to xh. So as our observation, these are equal. So this is equal to h. Therefore, x belongs to h. Please check the converse part proof. Any doubts? If you are clear, I will prove the main part. Right. So let us go with the main part. So you assume that x belongs to h. So we have to prove xh is equal to h is equal to hx. So here my intention is I want to prove xh is equal to h first. Then similarly we can prove that h is equal to hx. Therefore the three will become equal. Agree? Yes or no? So if you consider the first part, xh is equal to h, this is a set, this is a set. If you want to prove that these two are equal, the general thinking is one is subset of the other. So you have to prove that xh subset of h and h subset of xh. That we have to prove. Okay? Now let us go with the part. So we have x belongs to h, we can write x is equal to xe belongs to xh. Therefore, h is subset of xh. On the other hand, let xy belongs to xh. Therefore, y belongs to h. Therefore, we can have x into y belongs to h since closure law. Therefore, h is subset of xh. Therefore, xh equal to h. Any questions or doubts? Please take a note of that. Now, can I take the other definition? Right. So, in the first part of main proof, why h is subset of xh? Right. So, is that your question, right? Why h is subset of xh? Am I correct? Yeah. Now see, if you write the element xh, then you are saying that I have taken only one element x belongs to h. So as I have written that x is equal to xe belongs to xh, because xh is nothing but x into something. Every element in xh will be of the form x into something. So initially I have taken x belongs to h and I proved that x belongs to xh. So I have concluded this part. So if you are not interested, if you say that h contains not only x, other elements also, how you can confirm that these other elements also belongs to xh? If that is your doubt, we can prove it in the other way around. Because let us say, if you take y belongs to h, if you want to say that h is subset of xh, I have to prove y belongs to xh. Do you agree? So that whatever the element you consider in h, that will belong to xh. Right. Now, if you consider y, that I can write it as identity into y, because identity into anything, you can get the same thing. So this is equal to x inverse y, because identity is nothing but x into x inverse, that you can write. So you can write it as x into x inverse y. So this value belongs to xh because the pattern of xh is nothing but set of all elements x into something such that this something belongs to h. So I have taken x in h, y in h. So x inverse also belongs to h by inverse law. X inverse y belongs to h by closure law. Therefore, x into x inverse y is of the form x into something. This something is belonging to h. Therefore, y belongs to h. Y belongs to xh. That's the key. You can write it as. Okay? Is that fine? So while proving h subset of xh, you take any other element y in h that you can manipulate like this. In the form of the conversion belongs to xh. Is it clear? Right. Now here I want to take one good result. Based on this, a previous question is also framed. Let me give you a note of that. If h comma k are finite subgroups of a group G, then order of hk equal to order of h into order of k by order of h intersection k. You take a note of this result. Based on this, we will prove a problem. And this is the problem based on this result. If h comma k are subgroups of finite group G such that order of h is greater than square root of order of G and order of k is greater than square root of order of G, then order of h intersection k is not equal to identity, or h intersection k is greater than 1. This is the problem. You please take a note of that. We will discuss the approach. After noting, please tell. Is it noted? Now here, whenever you take a group G, here I have taken two subgroups for G. Let us say H is a subgroup here and K is a subgroup here. Here HK is nothing but the product of the two sets. So you can consider a big set than these two. This is the product set. We don't know whether this product is equal to G or not. So we can say HK, if you consider it is a subset of G. It may be a proper subset or sometimes it is equal to G. We accept it. So from this point, we can say that order of G is greater than or equal to order of HK. Because this is the group and this is the subset. So group order will be always greater than or equal to the subset order. From this point. Here we got an expression for the product set. The order of the product set, we got an expression. Substituting this, it is order of H into order of K by order of H intersection K. In the problem, it is given that subgroup order is greater than square root of group order. So using this technique here, it is greater than square root of order of G into square root of order of G by order of H intersection K. This is equal to order of G by order of H intersection K. This expression you are seeing, or the first one, this part you are saying. Say, yeah, this is the result. I have given the result for you as a note condition. If you want the proof, I will give the proof for you. As a post in Telegram, you can observe the proof. Okay? Right. I will give the proof for it. Right. Now, from this relation, you can say that order of G is greater than order of G by order of H intersection K. If this inequality to be true, then obviously the denominator must be greater than 1. If the denominator is 1, we can say that order of G is greater than order of G. It is a contradiction. We accept it. So, in order to satisfy the inequality, the denominator must be greater than 1. That is the solution of the problem. That's it. Is that clear or not? Please tell. Any questions or any doubts for anybody? So can I take the other? So that we can take as a confirmation. That we can take a confirmation. So here there plus means addition of the sets. So that we have to consider it. So if the operation is plus, apart from taking division, we should have to take minus. If you treat that plus is nothing but union of the sets, it is just like n of A plus n of B minus n of A intersection B. It is just like that. Because if, please understand that in the definition, this is the operation dot. So you are replacing dot with the operation plus. So the respective thing you have to do the same thing here. So this should be plus, then division must be replaced with minus, the equivalent symbol. You agree? Isn't it? That's it. It is just like rewriting the formula n of A in B is equal to n of A plus n of B minus n of A intersection B. It is just like that. Okay. I want to take the other problem. There we conclude our today's class session. It is also one of the application of the above formula. You please take a note of this. We discuss the approach. After noting, please tell. Right. Now here what is given? I took a finite group with order PQ. So you can say order of G is equal to 15. So 3 5s. 3 is a prime number, 5 is a prime number. Just like that. Or 5 3s you can say. So the order of the group is product of two primes, where these two prime numbers are distinct prime numbers and one prime number is bigger than the other. So in this case we have to show that if you calculate the subgroups of G, you can find at the most one subgroup having order P. So if you say order of G is equal to 5 into 3, so you can find a subgroup with order 5. So that type of subgroup may exist or may not exist. If you want to calculate the number of subgroups with order 5, you can find maximum one subgroup. You will not get two subgroups. That is the context of the problem. Is it clear? Right. So the logic is very simple. Initially, I consider that there are two subgroups. And I prove that they are becoming equal. It is not a silo theorem, it is different. See, I have given the result here. Based on this result only, I am solving this problem. Please understand. That's why I didn't erase this result. I am solving this problem based on this result only. This is not silo theorem, it is different. Is it fine? Yeah. So here, let H and K are two subgroups with order of H is equal to P, order of K is equal to P. So my target here is I want to show H is equal to K. So what happens? G will have exactly one subgroup of order P. This is the whole logic. Okay? Yes or no? Right. Now, as we know that intersection is a subgroup of H. We accept it or not? Yes. So, by Lagrange's theorem, order of H intersection K divides order of H. As we have taken that order of H is equal to P, this implies that order of H intersection K must be equal to 1 or order of H intersection K will be equal to P. Agree or disagree? Because P is a prime number, order of H is equal to P at this point. So if you take that order of the intersection is 1, then order of Hk is equal to order of H into order of K by order of H intersection K. This is equal to P into P by order of H intersection K. And this is greater than PQ. This is equal to order of G since P is greater than Q is given. So which is wrong? Are you getting the idea? So here intersection is a subgroup of the group. H intersection K is a subgroup of H. Since by Lagrange's theorem, subgroup divides group order, order of H intersection K divides order of H. So the only possibility for the intersection is either 1 or P. The total number of elements in the intersection must be either 1 or P, because P is a prime number here. If you take that intersection contains one element only, so you have a formula order of Hk is equal to this. Here this part is nothing but 1. In the numerator you have P into P, P square. So in the problem it is given that P is greater than Q. So for 1 P you can see it is greater than Q, it is greater than PQ order of G. So what it is, you got the result that order of Hk is greater than order of G. This is wrong because subgroup order is bigger than group order. This is not practically correct because Hk is a subgroup. So subgroup order is greater than group order, which is practically not correct. This is a contradiction. Therefore, the only possibility is order of H intersection K is equal to P. Are you getting? So here what happens, we can say H intersection K is a subset of H, H intersection K is a subset of K. So please understand that H, K, H intersection K all are having same number of elements. So H contains P elements, K contains P elements, intersection contains P elements. Hence we can say that H is equal to K is equal to H intersection K. So as we have proved that H and K both are same, so there is only one subgroup of order P. That's all. That is the conclusion of the problem. So if you look at the ideology, I have to show there is only one subgroup of order P. For this, I have taken two subgroups. My intention is these two are equal. As I know, intersection is a subgroup. So I have taken that intersection order divides group order by Lagrange's theorem. So the only possibility for the order is 1 or p, because p is a prime number. So if you take intersection contains only one element, you are getting a contradiction that subgroup order is bigger than group order. So that is not practically correct. So the only possibility is intersection contains p elements. It means that the subgroups H, K and intersection all are having equal number of elements. If all are having equal number of elements means all are equal, same. H, K, intersection all are same. Therefore you have H is equal to K. Hence there is only one subgroup of having p elements. That is the conclusion. Okay. Any questions? So this is the conclusion of the problem. Let us wind up right now, and tomorrow we will meet with the new concept. Is it fine? If anybody has any other questions, you can ask. Do you have any doubts for the approach of this problem? Anybody? So for this problem, I will give the posters in Telegram. You can check that. After the class, you can check that. I will give the posters in Telegram. The proof, how it is defined. The proof is not important for you with regard to exam point of view. But if you are interested, you can learn that.